Hello, I'm Sridharan, and my project is on the neurobiology of voluntary exercise, a novel approach to alleviate chemobrain by promoting hippocampal neurogenesis. So, a little about myself. I'm a rising senior at Little Rock Central High School in Little Rock, Arkansas, and I'm heavily involved in science fair. I've done ISA for many years and won grand and special awards, as well as national JSHS. I do biochemistry research at UIMS in the Department of Pharmaceutical Sciences, and I play the mridangam, which is the double-sided instrument of Carnatic music. And finally, I started a nonprofit to serve the community, Little Rock community, through conducting music concerts, whether it be Carnatic or Western classical music. So to begin with my project, I start with Chemobrain. So chemotherapy, while saving many cancer patients' lives, has resulted in about 78% of all cancer patients reporting some form of cognitive decline or impairment, otherwise known as chemobrain. Now, chemobrain has been proven to persist in cancer patients up to 20 years through and after treatment, therefore significantly affecting the quality of their lives as well as in survivors' lives. Now, despite decades of research, a safe intervention to alleviate chemobrain has not yet been proven, this due to its underlying molecular mechanisms not being well studied. Now, voluntary exercise emerges as a non-invasive mode of treatment as it's able to target anti-inflammatory and cytoprotective genes through various signaling pathways, and has even been proven to promote hippocampal neurogenesis in stable conditions by altering the gut microbiome in order to release beneficial molecules to signal to the hippocampus to decrease inflammatory responses by modulating microglial activity. So the main purpose of my project is to decipher the neuroprotective effects of voluntary exercise on chemobrain, and I hypothesize that voluntary exercise will be able to do so by promoting hippocampal neurogenesis through anti-neuroinflammatory effects. So to begin, my experimental setup was that C57 black 6 female mice were single housed in cages with or without a running wheel, and the mice were given either 8 once-weekly intraperitoneal injections of the ACT treatment regimen or saline injections for the control mice. Now, the ACT treatment regimen was chosen as chemobrain affects breast cancer patients the most, and ACT is the most common chemotherapy treatment regimen for breast cancer patients. The experimental design of my project consisted of 8 weeks of total chemotherapy treatment, with the first 4 weeks consisting of doxorubicin and cyclophosphamide treatment, and the final 4 weeks consisting of paclitaxel treatment. Then a 30 days resting period was given for the effects of the treatment to settle in, as well as for the mice to voluntarily exercise. And then Morse-Water maze behavior was conducted, and finally the mice were euthanized, in which the tissues for experimentation were collected along with fecal samples. Now, this is a little workflow of the various experiments that I did in my project. So to begin with, I started off with the Morse water maze, which is a behavioral test that is used to study hippocampal dependent spatial memory in mice. So as you can see, a mouse that's cognitively impaired will travel more distance and take more time to find the target platform submerged underneath the water, therefore showing poorly encoded memory. Whereas a mouse that's not cognitively impaired will take less time and less distance to find the target platform, therefore showing a better encoded memory. And Morris Watermay's results revealed that chemotherapy significantly decreased the percentage of time spent in the target quadrant, whereas voluntary exercise was able to significantly increase the percentage of time spent in the target quadrant, thereby suggesting that voluntary exercise is able to ameliorate deficits in hippocampal dependent spatial memory caused by chemotherapy treatment. Now, in order to gain a structural and molecular understanding of this effect, I then conducted Western blotting analysis on the protein expression of brain-derived neurotrophic factor, BDNF, as well as neuronal nuclease, NeuN, in order to study synaptic plasticity and mature neurons respectively. Since chemotherapy treatment caused a decrease in NeuN expression, therefore mature neurons were decreased, BDNF expression was therefore decreased in tandem as there was a resulting less synaptic plasticity, whereas voluntary exercise was able to maintain the overall expressions of NeuN and BDNF post-chemotherapy treatment. For the expressions of GFAP and double cortin, which are markers for astrocytes and neurogenesis, chemotherapy treatment had the same effect, a significant decrease in both GFAP and double cortin expression, whereas voluntary exercise was still able to increase the overall expressions and stabilize them. IBA1 expression, on the other hand, was overexpressed due to chemotherapy treatment as a result of microglial activity due to neuroinflammation. But voluntary exercise was able to provide the same effect, stabilization of IBA1 expression. So in essence, voluntary exercise is able to establish a proper microenvironment for neuronal growth in order to maintain neuronal homeostasis post-chemotherapy treatment. Now, very few studies have used the omics technology as a tool to study chemotherapy-related side effects, particularly chemobrain. Hence, I then conducted proteomic analysis of the hippocampus tissues in order to study significantly affected pathways and proteins as a result of both modes of treatment. Now, the first network here is the protein network of the ACT treated group quantified versus the saline treatment group. And the second network is that of the ACT treated group that was able to voluntarily exercise quantified versus the ACT alone treated group. And the IPA analysis revealed that the most significantly affected pathway was indeed the inflammatory pathway. Particularly, ACT treatment was predicted to inhibit TGF beta expression, and voluntary exercise post chemotherapy treatment was predicted to inhibit TNF alpha and interleukin 1 beta expression. To validate the results of my proteomics analysis, I then conducted QRT-PCR in order to study the gene expressions of the three inflammatory pathway-related proteins from my networks. TNF and interleukin 1 beta expression were significantly overexpressed due to chemotherapy treatment as a result of increased neuroinflammation cascades. Whereas predicted by the proteomics results, voluntary exercise was able to inhibit such an increased overexpression of both pro-inflammatory cytokines. TGF-beta, on the other hand, is known for its anti-inflammatory effects. Now, as predicted by the proteomics results once again, TGF-beta expression was significantly downregulated due to chemotherapy treatment, but voluntary exercise was able to induce TGF-beta expression and stabilize it across the table. TNF and CD68 expression, which is a marker for specific microglial activity, was once again overexpressed due to chemotherapy treatment as a result of those cascades, whereas voluntary exercise was able to heavily decrease and stabilize TNF and CD68 expression, not only validating the results of my proteomics, but also establishing a novel pathway of action for the neuroprotective effects of voluntary exercise on chemobrain. Now, finally, I studied the effects of voluntary exercise on the gut-brain axis, which is the bidirectional communication between the gut microbiome and the brain. So the taxonomy bar plots of the chemotherapy-treated mice shows a disturbed diversity in the presence of species in the gut microbiome compared to the stable diversity in the other treatment groups, particularly between the phylum Firmicutes and Bacteroidetes, which suggests a negative impact on the gut-brain axis. Moreover, alpha diversity metrics of Fate's phylogenetic diversity and Chow-1 species richness revealed a decreased diversity across evolutionary lineages as well as overall species richness due to chemotherapy treatment, which was significantly ameliorated by voluntary exercise. Finally, beta diversity metrics of Jacquard Emperor, weighted unifrac, and unweighted unifrac showed increased dissimilarity and separation across the composition of the gut microbiome due to chemotherapy treatment. But once again, voluntary exercise was able to significantly alleviate that by providing beneficial effects on the gut microbiome. So my study revealed that voluntary exercise is able to alleviate deficits in hippocampal dependent spatial memory by promoting hippocampal neurogenesis and a proper microenvironment for neuronal growth. Moreover, voluntary exercise was able to provide neuroprotective effects through anti-neuroinflammation by modulating the gut-brain axis by providing robust effects in the gut microbiome. So in conclusion, voluntary exercise was able to promote hippocampal neurogenesis through anti-neuroinflammation in order to alleviate chemobrain. And the implications of my project are vast. Voluntary exercise will be able to decrease that high prevalence rate as well as persistence rate of chemobrain from 78% and 20 years post-treatment down significantly in order to decrease breast cancer-related hospitalization rates, but also enhance the overall health of the general population. So my project reveals that voluntary exercise is a novel and powerful approach to ameliorate chemobrain in breast cancer patients. In the future, I'd like to study the effects of voluntary exercise in combination with diet enrichment on chemobrain in breast cancer-induced mice. And these are my selected references. I'd like to thank my mentor, Dr. Antonio R. Allen and Bailey Cronin for substantial support and guidance throughout my project, as well as for handling live mice and harvesting all the tissues for my project. Thank you so much for listening to my presentation.